What is SystemVerilog? HDLs like Verilog and VHDL, they have their own limitations. Basically, HDLs are static in nature, so they consume a lot of memory. What it means is you have to define everything upfront while writing the source code. You write the source code and then you compile. During compilation, the simulator is going to elaborate the design, and then eventually it's going to create the internal data structure for the test benches that you have created and for the designs that you have created. So later on, while running simulation, if you want to change certain things dynamically, it would be impossible in case of HDL. So that's a big limitation. Randomization. There are very limited features available in HDL. You won't be able to randomize the complete packet. That's not possible in Verilog. You would be able to randomize only variables. So how we can do this in SystemVerilog? That's what I'm going to show you. HDL support only code coverage. We can use code coverage mainly to verify the quality of test bench, whether the test bench is really good enough to execute each and every statement in the RTL, or each and every branch, or each and every state in the finite state machine. That's what code coverage does. But if you want to understand whether we have verified all the design features, or with respect to design verification, how much we have done, have we completed 60% verification or 80% verification? How much more is pending with respect to verification sign off? We won't be able to use code coverage. There we need functional coverage. Also, when it comes to creating a reusable test bench in HDL, it's really difficult because this language doesn't support programming features like object-oriented programming. So we are going to discuss how we can create the reusable test benches beautifully using object-oriented programming. All right. What is SystemVerilog? I would say SystemVerilog is nothing but the latest version of Verilog. So a set of extensions to Verilog 2001. And it's an unified language for design and verification. You can do pretty much everything for system level design. You can use this language for RTL, you can use this language for test benches, you can write assertions, you can do assertion-based verification, you can create even functional models. So look at this, this language supports all these verification methodologies: constraint-random coverage-driven verification, assertion-based verification, functional coverage. So you would be able to make use of all these methodologies to verify any kind of IP or subsystem or SOC. And SystemVerilog supports object-oriented programming. We will discuss about it. How we created this language? What are the sources? So basically, SystemVerilog is an IEEE standard language based on Verilog 2001. SystemVerilog extensions come from various languages. Languages like C, C++, PSL, Vera, VHDL. Look at this. There are a lot of new data types from C, C++, and programming methodologies like object-oriented programming. They are mainly from languages like C++. Assertion-based verification primarily from the language called PSL. So we have a feature called SystemVerilog Assertion as part of SystemVerilog. Now you don't really need to go for separate languages like PSL. You can define all the assertions beautifully in SystemVerilog itself. And constraint-random simulation. For that, you may want to generate random values, and all the concepts like randomization and constraints, they are from the language called Vera. And even there are really good concepts like enumerated data types or packages or libraries. They are all from the language called VHDL, and direct programming interface from Synopsys. So we have considered all good features of various languages, and then we have implemented everything as part of Verilog. This is how Verilog emerged as SystemVerilog. So I would say like SystemVerilog is the latest version of Verilog. This is how Verilog evolved. It started off with the version 1995, and then it became 2001, and then it emerged as SystemVerilog. So this was the transition, Verilog to SystemVerilog. The version was 3.0, and then it became SystemVerilog IEEE 1800 2017. This is the latest version of SystemVerilog. So basically SystemVerilog is an IEEE standard language. That's a huge advantage. All right. These are all some of the good references. The best reference is LRM, Language Reference Manual. You can download the language reference manual from Accelera, Google for Accelera. You would be able to find the PDFs. That's like golden reference. If you want to understand any language feature, I would say you refer language reference manual. And then you want to understand more of the language features, especially how you can use these language features to implement the test bench, then I would say like you refer verificationacademy.com. The more you spend time on this website, you will be able to emerge as hands-on engineer. Also, there are good textbooks available in the market. Writing Test Benches in SystemVerilog by Janik. The other one is SystemVerilog for Verification by Chris Beer. Then why this course? You have Verification Academy, you have good textbooks available in the market, and how this course is different from all these references. Look at this. This course is completely based on test bench implementation, how you can implement test bench. That is the main objective. So we don't want to discuss the language features and concepts like bits and pieces. Every time when we discuss any particular language feature or the concept, we will show you like this is how you are going to apply this concept and create the test bench. So throughout the course, we will use same example. So in this course, we are going to use two kinds of examples. One is the small one. It's a dual port RAM. It's basically a memory. And for this memory, how you can create the test bench. This is the example we would be using throughout this language course. So while learning the language concepts, you will look at like how the generator can be created, how the driver can be created, how the monitor can be created, and how you can make the connections through mailbox. And then eventually how you can instantiate all these lower level components as objects as part of the environment, and how you can build the complete environment. That's how the course is going to happen step by step. At the end of the course, you will have the complete idea like how you can build this reusable verification environment. At the same time, I will show you how you can use the language features to verify complex designs like SOC. So I'm going to show you the big picture, because you might not be able to apply all kinds of language features on a small design and explore. Certain features might be irrelevant for small design. For example, if you really want to understand the need of interface and why we have concepts like static interface and virtual interface, that's where you really need to look at complex designs like SOC. So I created a beautiful example. The design is called Maven SOC. This SOC will have various IPs, and I'm going to show you like how the IPs can be connected with the help of on-chip bus, and then eventually how you can create even test benches for the same SOC. So in this case, you are going to understand like how you can implement test bench for this small design, dual port RAM, and then eventually how you can scale up this architecture to a bigger designs like SOC. So from this architecture to SOC architecture, how you can scale up, how you can migrate, that's what I'm going to show you. So you will have two different perspectives, like how you can apply all these language concepts and implement test bench on your own. That's where you are going to use small design. At the same time, in real time, how we can apply all these language concepts and features to create complex test bench like test benches for SOC. All right.